Welcome to School of Computing. In today's session, we will try to understand implementation of red-black tree. In our previous session on red-black tree, we have discussed in detail what exactly is a red-black tree and how a red-black tree is constructed. A quick recap of the key points need to be considered while constructing a red-black tree. The root node must be black. Two consecutive nodes, that is parent and child, cannot be red. It's a violation. If two consecutive red nodes are found, we either recolor or perform a rotation operation depending upon the uncle. We used the word uncle to refer to the node which is sibling of the parent. So if the uncle is red, recoloring is done, and if uncle is black, rotation is done. And all leaf nodes, very specifically leaf nodes here, I am referring to the child of leaf. So as such, the child nodes of leaf does not exist. Leaf nodes are the nodes for which there are no children. In red-black tree, we assume those children of leaf which do not exist. We assume them as if they are existing, and we call them nil nodes or null nodes, and we treat them as black nodes. And when we construct our red-black tree using these rules, by following these rules, we need to ensure that the number of black nodes from the root to any leaf must be same. So at the end of the construction of RBT, if you check the number of black nodes from root to every leaf node, you should be able to get the same number of black nodes. If you did not see the same number of black nodes from root to every leaf node, it means there was some error in the construction of red-black tree. So for a given sequence, how to construct a red-black tree was discussed in detail in one of our previous session on red-black tree. And in continuation to that session, we try to understand the implementation of red-black tree in C language in today's session. So moving forward, in red-black tree, we are using two notations, like every node is colored. We assign two colors, either red or black, to the nodes in red-black tree. Only two possible colors are there, so we would like to enumerate. So we know what is enumeration. Enumeration is collection of some items or collection of some values which are known in advance. So for that we have a data type in C called as enum. It is similar to structure. Enum is also a user defined data type. So enum means I am defining my own data type called as color. So here capital letter C is their color. It refers to a data type, and in the flower brackets we have mentioned red comma black. It means that color is a data type, but it will allow only two values, either red or black. So that is the purpose of enum. And coming to the node type, in red-black tree, the members of the node are data, which is common in every tree. We have seen there is one data item. So int data is my data part. to give color to the node, I am creating a variable called as color. So please observe here the COLOR small letters, the one which is selected here, COLOR, this is a variable. COLOR in lower case is a variable. Color is a variable of type color. What is this capital C color? It is the data type. So color is a variable of type color which will allow only two values, either red or black. Then in the red black tree, every node will have a reference to its left child, a reference to right child, which was there in our AVL tree, it was there in binary search tree. Apart from a reference to left and right child, we also consider a reference to the parent of the node. So for every given node, there will be a left child and right child. Of course, they may exist or not. If it is existing, we will record the address. If it is not existing, we will write null. For every node, we have a left pointer, right pointer, capable of pointing to left and right child. Apart from that, in red black tree, we also maintain another pointer or a reference to the parent of the particular node. So why the parent of a particular node is important in our red black tree? The reason is, whenever there was a violation, parent is red and the child is also red, two consecutive reds, right? Whenever there is a red violation appears when there are two consecutive reds. Consecutive red means parent is red and immediate child is also red. So when there are two consecutive reds, it is red violation, and which is not allowed in a red black tree. So when violation occurs, then what we do is we have to modify the tree by performing either recoloring or rotation. Now in that process, to come to a conclusion whether recoloring has to be done or rotation has to be done whenever there is a red violation, the decision is taken based on uncle. So whom we call as uncle, we know very well. Uncle is the node which is sibling of the parent. So that's the reason I need to have a reference to my parent node also, so that I will check whether there exists a sibling to the parent or not. If the sibling is existing, then I'll check the color of the sibling. Sibling of parent is nothing but uncle. So if uncle is existing, right, and if uncle's color is red, we go for recoloring. And if uncle does not exist, we treat it as black. And when it is black, we go for rotation. Even if uncle is existing and it is black, then again we will do rotation. Only when uncle is red, we go for recoloring. And in detail we have discussed with couple of examples in our previous session on construction of RBT, how exactly recoloring is done, how exactly rotation is done. We have discussed in detail, and I hope you are aware of that particular process. So moving forward, struct node star root equal to null. You know, initially I created a global variable called as root, which is initially null. Now there are several functions in this program. Some of them are already used in our previous examples, in our previous concepts, like rotations we have already done in AVL tree, height calculation we have already done in AVL tree, creating a new node we have done in AVL tree, and binary search tree. So the functions which are used in this particular program are create node function, height function, left rotate and right rotate function, and insert function. There is a function called as a fix insert function, and for displaying the output of RBT we have print given level function and a display function. So among these 6 or 7 functions, right, the most important and functions which are new to us are insert and fix insert. Most of the other functions are more or less similar to our AVL tree implementation, right, for which we had a detailed discussion in our previous lectures. You can refer the uh, lecture on AVL tree implementation for in detail discussion on left and right rotate functions. And of course in theoretical implementation of AVL tree also we have discussed in detail the rotations, and even in previous session on RBT construction of red black tree I have discussed rotations, all 4 types of rotations. So moving forward, create node. This is a function in which we actually allot memory by using malloc. So whenever user opts for insert operation, you know that we are regularly following the concept of creating a menu driven program. So in the menu we give options like insert, display, then exit, like that. So our programs on all data structures were menu driven, and we run an infinite loop till the user opts to exit. We run an infinite loop and we'll ask user to enter the inputs. So suppose if user opted for insertion, definitely a new node has to be created. So that creation part is actually done by create node function, and if you observe carefully the line number 1 in create node function, we have malloc of size of struct node. You also know very well malloc always performs memory allocation. Of course memory allocation is the job of OS. malloc is a dynamic memory allocation function which will make a request to operating system on behalf of you, and memory allocation is done. And you always know, you also know that malloc returns the starting address of the memory which was allotted to you, but it returns the address by keeping it in a void pointer, because malloc don't know what is the purpose of the memory which you have actually created. Only the programmer knows why he has asked for 100 bytes, 200 bytes or 400 bytes. malloc really don't know. So malloc keeps that starting address in a void pointer. We have to convert that into an appropriate pointer. Since this piece of memory actually points to a node, it's a node, right? So we converted that void pointer into struct node star. So this struct node star is there, right? It is typecasting. I am converting void pointer into struct node star, means I am converting it into a node type. Now in that newly created new node, in the data part I am storing the data which is passed as parameter from the user. Color is red. By default every newly created node will be treated as red. Of course if that newly created node is root, we will convert it back to black, but however except root node, for every newly created node we give red color. And initially, as you remember the structure, we have data, color and 3 pointers, left, right and parent, and initially we put a null in all these 3 pointers. So you can see new node hyphen left equal to new node hyphen right equal to new node hyphen parent is equal to null. I am doing a multiple assignment in a single line. All 3 pointers are initialized to null, and that newly created new node, its address is returned by the create node function to its caller. So who called create node? Actually create node was called from insert function. So let me take you to the main function so that you can understand the structure of the program. So this is main function. We are running an infinite loop and I am creating a menu there, insert, display and exit. We ask user to enter the choice, we collect it in our choice variable which will be running inside a switch case. And in the switch case, under case 1, I am asking user to enter the value, I collect it using scanf and I am calling a function called as insert function. So first option is insert, so case 1 is insert function. Similarly, case 2 is display, so I am calling print tree aligned is one function which I use to print my tree. Since in order to print the tree I should know the starting node, so the root will be passed as input to the print function. Case 3 is exit. Exit is a built-in function present in standard library stdlib.h. So whenever user opts for exit, then I will come out of the program. So to terminate, to exit from the program, we have an option called as exit. So in the menu I will show insert, delete and exit option. 1, 2, 3. 1 is insert, 2 is display, 3 is exit. And by any chance, if user intentionally or by mistake, if he gives a number, when we ask him enter any choice, he should give either 1 or 2 or 3. By any chance, if user enters any other number, then it will land into the default case where I will print a message invalid choice. So this is our main function which runs on a switch case, and it's an infinite loop. When user opts for exit option, because of this exit function I'll be able to come out of that loop and I will be able to come out of the program as well. Now look at case 1. There is an insert function, right? So whatever value user has entered, that is passed to insert function. So we have to visit the insert function now. So this is the insert function, void insert int data. So the moment insert function was called, look at line number 1 inside insert function. Immediately we are calling create node function, and we have just now seen what create node function is doing. It is using malloc to do a memory allocation, store the data, give initial color as red to the newly created node, and initialize all 3 pointers left, right and parent with null. And finally create node returns the address of the newly created node, which is collected in a variable called as z in our insert function. And node y is initialized to null and struct node star x is equal to root. You know very well, first time when we are calling the insert function, root will be null because there is no element existing, no node is yet created, so initially it will be null. First time when insert function is called, then root is null. But second time when insert function is called, obviously root will not be null. Now while x not equal to null, since I am running it first time, this condition will fail. X not equal to null. No, x is equal to null. So I will not enter into this while loop. And z-parent is assigned the value of y, which is null initially. Now if y is equal to null, this condition is true now. What is y value? Y value is null. If y is equal to null, z is becoming the root. Z value is assigned to root. What is there in z? Just now we have seen what is there in z. Create node function's output is there in z. What is create node function doing? It is creating a new node and returns the address in z. So obviously when first time I am running the insert function, right, the newly created node is present in z and its address is copied into root. Means now root node is not null, it is pointing to the newly created node. Okay. Otherwise if the data is less than y hyphen data, what do you mean by y hyphen data? Means y is representing the already existing node and I am comparing the data. So if the newly means the data which is about to enter, the second insert or third insert, whatever it is, the incoming data, if it is less than the existing data, then it should become the left child, right? That's the reason z is becoming left child. Suppose if the incoming data is greater than the current existing node, then z should become the right child of it. That's the reason this last else part. So I hope you understood what the insert function is doing. Insert function, if I have to summarize it, insert function step 1, it creates a new node with the help of create node function. Then it collects that newly created node's address in z variable. Then it will check what is the previously inserted data. So it will compare the newly created z with the previous one. If it is less than that, the newly created value will become left child of the previous one. If the new value, just now created value which is there in z, if it is greater than the previous one, then it will become the right child. That is what we have done in the insert function. But there is an important point to be noted. What is that important point? We are just inserting a new node either to the left or right side based on the binary search tree rule. So if incoming value is less than the parent or the previous one, it should become left child, otherwise it should become right child, and of course no duplicates are allowed. That part is taken care in the insert function. But in red black tree, whenever a new record is inserted or whenever a new node is inserted, we also need to check, is it violating any two consecutive reads problem. If there is a violation, then I should go for recurring or rotation. That part, the core logic of RBT, is taken care by this function called as fix insert. And what I am passing as parameters to fix insert, if you observe carefully, both are addresses, because what is root? Root itself is a pointer. Struct node star root we have created. Root itself is pointer pointing to a node. Generally root will point to the root node. Now what do you mean by ampersand root? Ampersand root means address of root. So root itself is a pointer. Of course pointer is also a variable. So that variable will also have some address, right? That address is called as ampersand root, and I am passing it as parameter to fix insert function. Similarly, another input is z. What is z? Z refers to newly created node. Z refers to newly created node, and z is also a pointer of type struct node star. So one is a double pointer, means one is an address of a pointer. One is a pointer which contains address of a newly created node. So I am calling fix insert function from insert function. Fix insert will actually check for violation. It will perform recoloring or rotation, whatever is required, and it will ensure that all those rules of RBT are actually followed. So the core logic lies in fix insert function. Before we move on, there is a height function. This we have used even in our AVL tree. So height of every node need to be calculated, and you know the logic for calculating the height. It all depends on height of left child as well as right child. So if I have a tree with two levels, then height will be calculated. Suppose if there is only one level, no children at all, then what will be the height? So if I have a tree with a single node, it has no children, only one node, still the height will be 1. So what we have to do is, whenever we calculate height, we have to calculate height as height of left subtree minus height of right subtree plus 1. That's the reason we are adding plus 1 here. So it's a recursive function call where we will calculate height of left subtree. We also calculate height of right subtree, and we will check which one is greater. It's not subtraction. We have to check which one is greater. So if left subtree height is 2, right subtree height is 3, I need to pick 3 only, right? The greater one. Then of course we also add plus 1 to it. So this height function, which is not new, we have been discussing it in both AVL and RBT. And our interest is in fixed insert, because actual rules of RBT, both recoloring and rotation logic, is present inside fixed insert. So friends, this is fixed insert function. So you have seen I was passing address of root. So root itself is one pointer. Address of a pointer variable can be stored in a double pointer. That's the reason we wrote star star root. And struct node z we were passing. Z itself is one pointer. So I am collecting it. Z itself is one address. I am collecting it in a pointer called as star z. So root is a pointer address of a pointer variable. So double pointer is required. For z, a single pointer is required, because it is not address of a pointer variable, it is value inside a pointer variable. So single pointer is enough. Now what I am checking in this while loop, please observe carefully. While z hyphen parent and z hyphen parent color is equal to red. So what do you mean by that? If both current node and its parent node, if both are red, then there is a RR violation, red violation. Okay, if there is a violation, then I need to do either recoloring or rotation. If there is no violation, I am not worried, I need not do anything. So if you look at this while loop, the while loop has started here. Now look at this while loop where it is getting terminated. The while loop got terminated here. So entire code is within that while loop. Outside the while loop I need not do anything, because if there is no red violation, you need not do anything. No recoloring, no rotation. You can continue with your insertion operation. But outside the while loop, one single line we have written, that is, finally, whenever you do a recoloring or rotation, you need to ensure one thing, that the root node must be black. So to ensure that, we wrote this one line, but otherwise the code inside while loop, entire code will come inside the while loop, because what is this while condition? This while condition is true, means there is a red violation. So I'll enter into the while loop. Yes, there is a red violation. Now see this if condition. If z hyphen parent double equal to, means equals to z hyphen parent hyphen left. So what do you mean by z hyphen parent hyphen left? Parent and parent of my parent is nothing but grandparent, right? And grandparent's left child is nothing but sibling. So friends, this is little confusing, but I'll explain it so that it will be clear. Suppose Z is the current node. Z is the current node. Look at this if condition, this first half of if condition. If Z is the current node, Z hyphen parent means what? Parent node of Z. Now what do you mean by Z hyphen parent hyphen parent? Obviously parent of Z hyphen parent. So if Z is the current node, Z hyphen parent means the parent node of Z, hyphen parent means grandparent. Where we are here, right? Z hyphen parent hyphen parent hyphen parent hyphen parent means father and grandfather. Grandfather's left child. So what do you mean by grandfather's left child? Nothing but he is sibling of the parent. So Z hyphen parent hyphen left, it's nothing but uncle, right? Now if Z hyphen parent double equal to Z hyphen parent hyphen left, then what we are doing? We are checking the color. So if this condition is true, it means that there is an uncle. Uncle is existing. And look at the color. What is the color of uncle? If uncle's color is red, what need to be done? We have to do recoloring. How recoloring is done? That entire process we have seen in construction of RBT video lecture. Same thing is being implemented here. So if uncle's color is red, we have to do recoloring. And remember, during recoloring what will be done? Who will be recolored? Three people will be recolored. Uncle will be recolored, parent of Z will be recolored, and also the grandparent. So three recoloring statements you can see. Z hyphen parent, parent will be recolored. So first line is to recolor the parent. If it is red, I am making it black. And Y is nothing but uncle. Uncle's color is also modified, and grandparent color is also modified. Otherwise means what? Otherwise means uncle is not red. Uncle is not red means uncle is black. Uncle is black means what should we do? We have to do rotation, right? What type of rotation? We have discussed in detail. Whenever we use the word rotations, straight away we have to do AVL rotation only. So you have to see what type of rotation is required. So if Z is equal to Z hyphen parent hyphen right, means you have a red violation, and if it is because of the right child, then it comes under RR rotation problem. And if there is an RR rotation problem, solution is left rotation. So we are doing a left rotation. Suppose if it is, means otherwise, if it is not a RR rotation problem, then it is because of the left child. Means I have a current node which is red in color, its left child is also red in color. Then it becomes red violation, but because of a left child. So it will lead to a problem called as LL rotation. And then I will be doing a right rotation, you know that. So this is right rotation function. And right rotation function, left rotation function are also present in the same program. And right and left rotation, the logic, how right rotation, left rotation is done, we have discussed in detail in our RBT construction and also during our AVL program discussion. So this is the else part, wherein what happens if the problem occurs on the other side. So same code but on the else part. So this fix insert will take care of all those recoloring and rotation operations. And finally we will ensure that always root node is black. So whenever you are trying to digest this code, please try to take a sequence of numbers, trace them, means first value, suppose 10 you are inserting. You see from main there is a call to insert, from insert there is a call to create node, then create node returns something, then insert returns something to main. You have to do a tracing, line by line tracing, then only you will understand clearly what the entire code is doing. So this is about insert function. And you have seen the printing function, which we have used also in our AVL tree. So print given level, with the help of spaces I am trying to align my output so that it will look like a tree. But however, it's not mandatory. You can even print an in order sequence of the output, that is good enough. So this is about the code and how this fix insert is actually working. The most important function in red black tree is the fix insert function. So that is most important. And height function we have already seen. So in red black tree, the most important functions are insert function and fix insert function. So this is about red black tree's implementation. So to summarize, we have implemented red black tree using linked list, enumeration and self-referential structures. Although the code seems to be very lengthy, but if you divide the program into set of functions and start writing those functions individually, it will not look like a very complex logic. I hope in this session you are able to understand the implementation of red black tree in detail. Thank you.